As we move toward making this idea of having a system with variables and constants, things that change depending on parameters, initial values that allow us to set things up to start, we want to use that to describe an epidemic passing through a population. We need to talk about what variables and what changes matter in there. So in class on last Thursday, before we all split for break, the populations that we talked about wanting to model, the things that we wanted to keep track of in any predictive model of an epidemic, started with the idea that you have a group of people that are susceptible to some disease. And maybe within that population, you have one or two people who have a disease. And so those, you begin with some infected population. And the infected, through contact between the susceptible individuals and the infected individuals, the disease is transferred, or the virus is transferred from an infected individual to a susceptible individual, and the susceptible individual moves into the infected group. And so there's a number of people who become infected over any day, week, month, whatever time period we want to do. So the fact that we're talking about this happening over time is why we started talking about discrete time step models in the first place, because we know that the number of people who are susceptible is going to decrease over time, and we can say that the number of people at any later time is equal to the number of people who are susceptible now minus the number who get infected. So automatically we know that we'll just call this S, susceptible at time t, is going to be the number of people who are susceptible at time 1 minus the change in the number of susceptible people, and this is those that get infected. So automatically we have begun to start casting this in the same sort of terms that the falling brick was in. The height was equal to the height that it was before minus the change in height. The number of people who are susceptible later is equal to the number of people who are susceptible now minus the number who get infected. So we'll call this population I. If you remember when we did this in class, we broke the susceptible population up into subcategories depending on whether they were more susceptible or not, the consequences of that. And let's just leave all that detail out for now. In fact, that may be something that you in icons want to fold back into your models as added layers of complexity. We'll build a simple model that allows us to answer some of the basic questions about the epidemiology of this, and then we'll ask you to go ahead and extend this model to answer novel questions that you have. The infected population has a couple of things that could happen to it. Somebody who has an infection can recover. So this is a transmission from susceptible to infected. And then there's a recovery rate, the number of people that recover in any particular time. And when somebody has recovered from a viral infection, in typical cases of things like flu, you have an acquired immunity to that particular strain. So there can be a recovered group as well that have received this acquired immunity. In the coronavirus case, there's some question as to whether the virus is mutating fast enough for recovered people to re-enter the susceptible population. We won't include that in our simplistic model, but again, it may be something that you want to consider as you go on and add complexity to yours. The other thing that can happen is that you could perish. And so we know that there is a mortality rate associated with this particular disease that we're trying to model, and it would be disingenuous to leave out that possibility. But this means that there are 4 separate populations that we need to track and 3 different transition rates that occur in there. Susceptible people can become infected, infected people can recover, and infected people can die. So if we're going to build this set of fundamental equations that govern this, the infected people at time t is going to depend on the number of infected people at time t. But remember, there's 3 things that are then happening into the infected population. So one thing is people are entering that population. So this can also increase by the number of people who get infected. And the number of people that get infected, well, we need a name for that. So let's call that the transmission rate. That can depend on a lot of different things, such as how many infected people are, the density, how much contact there is between the infected people and the susceptible people, the weather, whether there's a quarantine in effect, how fundamentally transmissible the coronavirus itself is compared to other viral diseases. So this may be a complex thing for us to figure out, but if we just call it a transmission rate, then we can include it as a variable or as a feature of this right now. Because we've now labeled it something, we can also do this. So this actually becomes the number that received the transmission, who received the virus. There's also then two other rates. So there's a recovery rate and there's a death rate. And so if I want to cover all of the different things that can happen to the number of people in the infected category, so they could become, it can increase by those that become infected, it can decrease by a recovery rate, and it can also decrease by those that don't recover. And so that means that in order to calculate the number of infected people at a later time, I need to know how each of those four fundamental things, three fundamental changes are. The other two are simpler because those two populations only have sort of input arrows into them. So if I wanted to write down what the number of recovered people is at time t, then that's equal to the number of recovered people at time t minus 1. In this case, it's going to be plus the change in the number of recovered people. And the number of dead people at time t is equal to the number of dead people at t minus 1 plus the change in the number of dead people, the death rate. Because these are now set up as discrete time step kinds of things, it suggests that we can calculate all these things with the same sort of table that we had before. So if we want to know time, in this case we can do it in days, 0, 1, 2, 3, 4, however long into the future we want to run this, that there are certain variables we need to keep track of. We're going to need the number of susceptible individuals. We're going to need the number of infected individuals, recovered individuals, and dead. So those will be our four discrete populations. We'll also need a recovery rate. Or I'm sorry, let's start with the transmission rate. So we'll also need a transmission. We'll also need a recovery. And we'll also need a death. And you can imagine how this will look based on what we did with the falling brick before. If we start with a susceptible population of 100 people and 1 infected person and 0 people in these other categories, that one person may transmit the disease to 2 others in the first day through contact, through sneezing, through however it is that this disease is communicable. Since there are no people in the recovered population, there won't be anybody who recovers, there won't be anybody who dies. But now because the transmission rate is non-zero, then the number of susceptible people will go down by 2, so this will become 98. The number of infected people will go up by 2. Nobody recovered, nobody died, so these are both 0. But now since there are 3 infected people in a population of a total of 101 people, those 3 people may communicate the disease to others. And so maybe they communicate it to 5 other people. I'm making up numbers here, But this is something that we're actually going to have to calculate and build into a simulation, into a predictive model as an equation that depends on other things, such as the number of infected individuals or the density or the, with some other fundamental rates. Maybe one of these people recovers. Maybe nobody dies in that first day. And so at the end of the second full day, so at day 2, the number of susceptible individuals will have gone from 98 down by 5 to 93. The number of infected individuals will be 3 plus 5 minus 1. This will be 0 plus 1. This will be 0 plus 0. And so we're starting to see how this would develop in terms of actually writing out functions for what each of these are.